So in order to solve problem 1.17, we must scale the driving force equation by including a new variable so that it's easier to work with the order of magnitude, as well as create our initial guesses for the molar fluxes of methanol and acetone. And not only that, but this by scaling this problem, it will make it easier for us to code it to get our final answer. So here I have drawn a schematic, and what this depicts is that the air is traveling above the screen, and within the screen there is an acetone methanol mixture, and the gas from the mixture is able to be released to the atmosphere, but no air is able to come inside the tube. And the problem has given us the Stefan-Maxwell coefficients for the three different binary mixtures. D12 is equal, the coefficient equals 848 millimeters squared per second. D13 is 13.72 millimeters squared per second. And D23 is 19.91 millimeters squared per second. And I would like to say that acetone stands for 1, methanol stands for 2, and air stands for 3. The problem has also given us the temperature and pressure, so the temperature being 320.5 Kelvin, and the pressure being 99.4 kilopascals, and our delta, which is the difference in height between our z and our delta up here, is 0.24 meters, which was also given to us in the problem. So in order to start solving, or in order to start scaling, we're going to be using equation 1.35, and we're going to be expanding this equation out. So we're going to start by saying dy1 over dz equals y1n2 minus y2n1 divided by cd12 plus y1 n3 minus y3n1 divided by cd of 3. So by writing this equation out, we're basically saying that we're going to be multiplying the molar fraction of acetone by the molar flux of methanol and subtracting the molar flux and subtracting the product of the molar flux of acetone multiplied by the mole fraction of methanol and dividing that by the concentration and the fit diffusivity of the binary mixture 1, 2. And then we're going to be also adding the mole fraction of acetone times the molar flux of air, subtracting that by the mole fraction of air times the molar flux of acetone, and dividing that by our concentration times the Stefan-Maxwell coefficient 1, 3. But we can notice here that N3 is going to be equal to 0. And N3 is going to be equal to 0 because the molar flux of air at the surface of the liquid is going to be 0. So we can go ahead and say that this is going to be equal to 0. And so our second equation is going to be dy2 over dz, and that's going to be equal to y2n1 minus y1n2 divided by cd12, and then subtract by y3 and 2 divided by cd2, 3. So basically what I've done for the second equation is that wherever there was a 1, I put a 2, and wherever there was a 2, I put a 1 to create our second differential equation. And we'll be using these two equations during our coding process to actually solve the problem. But for now, what we're going to do is introduce a new variable called eta. And so eta is going to be equal to z over delta. And what eta is it's a unitless variable, and it ranges from 0 to 1, which is definitely easier to work with compared to 0 to 0.24. So here, what we're going to do is say that dy1 is dz is equal to dy1 over d eta times d eta over dz. And d eta over dz stands for 1 over delta. 1 over delta. So what we have basically written here is that dy1 over dz is equal to dy1 over d eta times 1 over delta. And if we were to go ahead and just, for example, erase the z from up here and just write eta and multiply that by 1 over delta, we want to move the delta over to the other side here, to the right side. So what we're going to do is multiply both sides by delta. So then we get a delta up here. So then dy1 over d eta equals delta times the first equation, first differential equation. And at that point, what we're attempting to do is create a new variable. So what we want to do now is actually move our delta to the right side. And since we're dealing with only one of the components of the first equation, I'm just going to go ahead and just start writing it with that only instead of the second component. So we could say dy over d eta equals delta times y1n2 minus y2n1 divided by concentration times the Stefan-Maxwell coefficient of 1, 2. So we have our delta here, and now what we can do is actually introduce our new variable, because what that's going to help us do is try to figure out an estimate for our mole flux of acetone and methanol, which are N1 and N2 in this case. So we can say F, for example, 1, 2 equals concentration times delta 1, 2, or not delta, the Stefan-Maxwell coefficient 1, 2 divided by our delta. And we can say that our concentration equals N over V, which is referring to Pivnert, our ideal gas law, and that also equals P over RT. And now what this helps us do is helps us simplify our created variable f of 1, 2. And we can say that since we want to make sure that all these variables have the same units and everything cancels out and works together, we could say that all the Stefan-Maxwell coefficients can be multiplied by 10 to the negative fifth. We can multiply the pressure from kilopascals by 10 to the fifth to convert to pascals, and we can also multiply the temperature by 10 to the third, because we're also multiplying that by our ideal gas constant. So we could put that in the right units. So since we have that all established, we can go ahead and say P, which is going to be 10 to the fifth, divided by RT, which can be 10 to the third, and we're going to multiply that by our Stefan-Maxwell coefficient, which can be 10 to the negative fifth. And keep in mind that this is just all an estimate, so it's just good enough for us during our scheduling process. And when we get that, when we multiply all these values together, we get 10 to the negative third. And that equals f of 1, 2. So now what we can do is go ahead and write our equation again and say dy1 over d eta equals y1 n2 minus y2 n1 divided by f of 1, 2. And since we know that this equals 10 to the negative third, and we know that the part on our left-hand side of our equation, the dy1 over d eta equals 1 because we're dividing out the delta, we can also say that n1 equals 10 to the negative third. So we could just say n1 equals 10 to the negative third. And since n1 and n2 we have established are on the same order, we can also say that n2 equals 10 to the negative third. So our final answer for the estimate of what the molar flux of acetone and methanol will be, the molar flux of both of them will be 10 to the negative third. And this will help us solve the coding part of our problem, which will be part 2.